Hello.
Hope you like this lesson.
Just for your reading pleasure.
That's the family's attempt to give you a little extra background noise for this lesson. And yes, I also hope you enjoy this lesson. We're looking at some more applications of derivatives through what we call Rolle's theorem and the mean value theorem. Now both of these are what we call existence theorems. They basically just state something exists, and then it's up to us to find it. There's certain conditions that have to be met before we can use them, and we'll talk about those. Rolle's theorem looks like this. It says let f be continuous, so f is some function that's continuous on the closed interval from a to b, and it's differentiable, which means the derivative exists on the open interval from a to b. Okay, so it has to be both continuous and differentiable. Both of those things are important. If either of those criteria are not met, either continuous or not differentiable on that entire interval, then we can't use Rolle's theorem. Okay, and here's what Rolle's theorem says. If f of a is equal to f of b, so basically we have equal y values, then there exists at least one number, we call it c, inside of that interval between a and b, such that the derivative of the function at that point c, at that x value c, is equal to 0. That is, there's going to be a horizontal tangent there. Okay, so let me just kind of explain a little bit how that might look. Okay, so let's say I've got some function, and I know that my f of a is equal to f of b. So, somewhere, I don't know where, maybe over here, I've got my a value, and somewhere over here I've got my b value. These are the edges of my interval. And if f of a is equal to f of b, so the y values at each of these points are going to be the same. They have the same y value. Well, if that's true, there's going to be some number c, and again, we don't know what it is, we don't know where it is, but there's going to be an x value in between a and b here. Where's my pointer? In between a and b, there's going to be some other value where the derivative at that number equals 0, which means there's got to be a horizontal tangent. Let's think about that. If this function is continuous and differentiable both, well, there's only a certain number of ways that can happen. Either it's going to come up like this and go through my f of a and come back down to f of b. There's going to be a horizontal tangent up here somewhere. Or it's going to come down like here and go back up. Well, it didn't go through b, but you get the idea. And there will be a horizontal tangent here. Or the only other option is that it's constant in here. And if it's constant, then it's obviously a horizontal tangent. And of course, it could do a lot of different things in here. It could go up and down and come back around. Either way, it's hitting the same point here and here at a and b. And so there are, in this case, several places where I would have a horizontal tangent. Here, 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 here. When the first derivative equals 0, we have a horizontal tangent line at that particular point. Okay, so that just tells us it exists somewhere. Somewhere it exists, and let's look at an example of how we would find that. Okay, so here's an example. We want to determine if Rolle's theorem can be applied to f on this interval from a to b. If it's not, we're going to explain why. So first we got to see if we can even use Rolle's theorem, and then why or why not. And if it can, then we're going to find that value c in between a and b so that the derivative is equal to 0. Okay, well, in order for Rolle's theorem to be true, let's check all our conditions. 1, is it let's go continuous first. Is it continuous? Well, let's think about it. We've got a quadratic here, x squared minus 8x plus 5. That's a parabola. We know parabolas are going to be continuous. So yes. Whoa. Sorry there. Don't know what happened. 2, continuous, yes. Differentiable. Okay. Is it going to be differentiable? Well, sure it is. We can take the derivative of all these terms. The only time it's going to be continuous and not differentiable is if we're going to have any vertical tangents or if we have any sharp turns. We're not going to have any sharp turns on this, so that's okay. And the last condition that must be met, well, in this interval, we got to make sure that our f of a is equal to f of b. And if that's not true, then we can't use Rolle's theorem. So let's check that. My a and b, this case, 2 is at the lower end of my interval, 6 is at the upper end. Let's evaluate both of those. So f of 2, plug that in here. We're going to take 2 squared minus 8 times 2 plus 5. And if we evaluate that, we should get, what is that? Negative 7. Okay, let's also evaluate f of 6. So this is going to be 6 squared minus 8 times 6 plus 5. What does that equal? Check those out, do the math. But yes, this does indeed also equal negative 7. So, there's our 3 conditions that must be met. The f of a has to equal f of b, provided that our function is both continuous and differentiable. And we said before, I think, if it's differentiable, it's automatically continuous. It doesn't go the other way. Not all functions that are continuous are differentiable. So be careful with that. But, okay, so now, all we've done so far is determine that, yes, we can use Rolle's theorem, so there is going to be some number in here that makes this true. Well, so let's find the derivative. The derivative is going to equal 0 somewhere in between there. We're just going to have to find the derivative, set it equal to 0, and solve for x to figure out what that value is. So the derivative of f of x is going to be 2x minus 8. Yes. So somewhere in between 2 and 6, this 2x minus 8 is going to have a horizontal tangent. Since this is the first derivative, we know we're going to have a 0. It's going to be 0 for the slope of that horizontal tangent line. Solving this for x would give us 4. Now, good idea to make sure and check. Is this x equal 4? Is this value in our interval even? And it is. 4 is in between 2 and 6. So, yep, there's our answer. X equals 4. This is our value of c that makes Rolle's theorem true. Okay, next let's talk about the mean value theorem, abbreviated MVT. Just like the intermediate value theorem, we can use IVT, does not exist. We can use DNE. These are common abbreviations. If you're asked to justify why something's true, MVT is certainly one of your possibilities that any AP reader is going to know what that stands for. Okay, now again, this is an existence theorem. This tells us just that something exists. It's similar to Rolle's theorem, but let's take a look at it and I'll show you the differences. It says if f is continuous, again, on a closed interval from a to b and differentiable on an open interval. And these are key pieces that, again, must be true in order to use the mean value theorem, must be continuous, and must be differentiable on some interval. Okay, then there exists a number c in between a and b, such that, and then we have this formula over here. So f prime of c is equal to f of b minus f of a over b minus a. Now, look closely at what we have here. This f of b minus a, I'll just pause it here a minute. You pause. Make sure you have this all written down so you can understand as I explain. Pause it longer if you need to. Okay, unpausing now. This over here, f of b minus f of a over b minus a. This formula should look familiar. Remember, these are y values up here. These are x values here, because this is my interval from a to b. What we have over here on the right, this here is the slope of a secant line. It's the slope of the secant line between a and b. Okay, this is our y minus y, y2 minus y1 over x2 minus x1 on my a and b. And this over here on this side, well, this is f prime at a certain point c. This is going to be the slope of a tangent line, because we only have one point here. A secant line, I'm given 2 points. It's going to be the points where the x values are a and b, and these will be the y values. I can find the slope of a secant line by just using our slope formula. Here, this is slope of a tangent line, because all I have is one value there. Okay, so what are we talking about? Let's say I have, I don't know, just something here. And let's say I want to look at the interval from, let's have A be right over here. And so it's going to hit about right there. And B is some value over here. And it's going to hit the graph about right there. Okay, so if I want to find the slope of that line, well, I've got an x and a y value here at this point, an x and a y value at this point. If I take y sub 2, which would be my f of b, minus f of a, divided by b minus a, I'll get the slope of this secant line, which would look something like that. Okay, so on this right side of the equation, I've got the slope of this secant line. Okay, so what the MVT tells us, the mean value theorem, is that somewhere between here and here, I'm going to have a tangent line that is going to be the same as this secant line, have the same slope as this secant line. And lines with the same slope are parallel. So I'm going to have somewhere in between here a line that's parallel to that. So let's think about how that might look. See if I can get a line parallel to it, or pretty close. Okay, so there's two lines that are parallel. Yeah, I got that closer than I thought. Okay, now I'm looking for somewhere in between A and B, in between A and B, in between here and here, I'm going to have a tangent line that has this slope here. So technically what I'm going to do is, well, let's take a look. It's going to be somewhere probably about right, boom, about right there. And so right in here, at this point, this is my point C. Because remember, slope means the first derivative is slope. Slope of a tangent line is right there. Okay, so it's got to exist in there somewhere. Similar to the Rolle's theorem, but our line doesn't have to be horizontal. We're looking at for any line, any secant line. Okay, now a good way to tackle these types of problems looks like the next slide. So, if we want to use the mean value theorem, here's some handy steps. First, find the slope of the secant line through the endpoints on the interval. The y sub 2 minus y sub 1. Now, if you're only given the x values, you're going to have to plug them into the function in order to find the y values. Then we can find the slope of that secant line. Then, find the derivative of the function. Now, we don't know what the c value is, so just find f of x. We haven't found c yet. Okay. So, find the slope of the secant line. Find the first derivative, and then you're going to set those two equal to each other. Once you set those equal to each other, then just solve for x. That x value is going to be your c that makes this true. And then, again, make sure that this value of c, or values, might have more than one, is in between a and b. It's in our interval. Now, just like with the Rolle's theorem, we have to make sure of certain conditions first. One, we have to make sure that it's continuous, and we have to make sure it's differentiable. Then we can find these other pieces. Okay, so here's an example. First, we want to determine if the mean value theorem can be applied to this function f on the interval from a to b, the closed interval, and if not, explain why. If it can, we're going to find c. We're going to find this value in between a and b on the open interval. That satisfies the mean value theorem. So again, we got to make sure of a couple things first. Pause if you need to. But we need to first find out and figure out, is it continuous? Is it continuous? Is it differentiable? Okay. Okay, so this is x to the fourth minus 8x. This is a polynomial. Polynomials are indeed continuous, so no problem there. Differentiable. This isn't going to have any sharp turns or any jumps or steps or anything like that. So yes, differentiable also. So, no issues there. So, let's now go ahead and use our mean value theorem. Erase this. So, we've got 0 is going to be our A, 2 is going to be our B. So, first off, I want to find the slope of this secant line that goes through 0 and 2 along the x. So, we need to find our y values for each of these. So, when A is 0, I'm sorry, yes, 0, my f of A is going to be f of 0. This is going to be 0 to the fourth minus 8 times 0, 0, f of B, or in this case 2, 2 to the fourth minus 8 times 2, well 2 to the fourth is 16, 8 times 2 is 16, that's also 0. So, looks to me like these are zeros of the function. That's going to cross the x-axis at both of these, at 0, 0, and 2, 0. Okay, so let's find our slope of this line. This is going to be 0 minus 0 for my y values. 2 minus 0 for my x values. Well, 0 divided by anything is 0. Okay, so it's not always going to be this way, but this one's going to be like Rolle's theorem in that this line is horizontal. Okay, So now we need to find our derivative of the function f prime of x. X to the fourth minus 8x is going to be 4x cubed minus 8. And then, to find out where my c is located, I'm going to set my derivative equal to the slope of my secant line. This is the slope of the tangent line, 4x cubed minus 8. I don't know where yet, some x value. This is the slope of my secant line, so I'm going to set 4x cubed minus 8 equal to 0 and solve for x. So 4x cubed will equal positive 8, adding 8 to the other side. Divide by 4. So x cubed equals 2. So x, of course, is going to be the cubed root of 2. Because I got to take the cubed root of both of these. Okay. Again, we want to check now, make sure, is the cubed root of 2 in between 0 and 2? Well, I would certainly hope so. Even if you don't know an approximation of that, we know the cubed root of 0 is going to be 0. We knew the cubed root of 8 is going to be 2. So this definitely falls in between those two. Don't know if you've done that before, but that's a good way to approximate and tell if something's in a certain range. So this is our value that satisfies the mean value theorem here. Now we've talked about, on these last two, determine if it can be applied. If not, explain why. Let's just discuss that briefly. Say I have, I don't know, maybe f of x equal to something like x minus 1 over x, and I want to use Rolle's theorem or the mean value theorem from the interval from, say, -1 to +4. Okay. Here's where can't use the mean value theorem here. And here's why. This function is not continuous for all values in this interval. If I'm dividing by x, x cannot equal 0 here. 0 is in this interval. So that makes this not continuous. This is not continuous at x equals 0. This would be our reason as to why I couldn't use mean value theorem for this particular example. Another, maybe I've got something like this. I don't know. Something with an absolute value. Because we know there are times when absolute value, say I'm looking at maybe the absolute value of x minus 3 on the interval from, I don't know, how about 0 to 5. I'm just making this up. But we know absolute value function, it's going to look something, it's going to have a v, it's going to have a sharp turn here. Still continuous, but can't use mean value theorem here because this is going to be not differentiable at x equals 3. Because at 3 I'm going to have a sharp turn here. My limit is going to be negative as I come from the left and positive as I come from the right. Okay. Just something to think about, keep in the back of your mind. A lot of the times these are going to be fine, but whenever a function's not continuous and not differentiable, we can't use the mean value theorem or Rolle's theorem. Here's your assignment. Give these a try. Page 174, 9 to 21 odd, 27 and 28. There's graphs that go along with those. It says on there to verify with the graphing utility. If you don't have one, don't worry about it. That's only part of the problem. The majority of the problem doesn't need a calculator. Same thing with 35 and 36. And then 37 through 45 odd, you're using the mean value theorem. Thanks.